In this series, we're building up a little 1-bit computer on the breadboard based on the Motorola MC14500, which is a 1-bit industrial control unit, but it has a lot of really interesting features. In the previous 2 episodes, we built a clock based on the 555 timer, as well as a program counter based on the 74HC163. We actually used 2 of them getting together to give us an 8-bit program counter. And so in this episode, I want to take the next step. So let's hop over to the bench, take a look at what we're going to build, and then we'll pull the breadboard out and get to it. All right, so here is our kind of blueprint that we're following along to build this up on the breadboard. And last time we built these 2 program counter chips here, and this gives us an 8-bit address that, as we can see here, feeds into a MCM7641. And looking up on the internet, that looks to be like a 4K programmable read-only memory, or a PROM. Now, I don't have any EPROMs in my collection, and I don't even have an EPROM writer. So even if I had an EPROM, I wouldn't have any way to get a program to it. So instead, I'm going to use this chip right here. Now, this is an AS6C6264. It's an 8K by 8-bit CMOS static RAM. Now, it may seem a little strange to be using a RAM chip where normally we should be using a ROM chip. And that's because you would write a program to the read-only memory, and then it would retain that program every time you power cycle it. But if we use a static RAM chip, every time we remove power from the breadboard, whatever program is in that RAM chip is gone. And furthermore, there's no real way to program a static RAM chip outside of the system. So I can't pull the static RAM chip out and plug it into a programmer and write a program on it. So the only way to program this static RAM chip is when it's on the board with power applied to it. And this sounds incredibly inconvenient, and it is to an extent. But I have some ideas about how we can quickly program this essentially program memory module in our system in the future. But for now, I think we're just going to pop this onto the breadboard and then maybe hook up some dip switches. And so we can flip the static RAM over to write mode and then store in whatever data we want to store by just using a dip switch. So if we look at the datasheet here, we can see that it kind of lists what each one of these pins are going to do. And so A0 to A12 are the address inputs. So this can actually use a larger program counter than the one that we are currently using. So we're only going to use 8 of those. And then DQ0 through DQ7 are the data inputs and outputs. So when we're storing, we'll put a value onto those pins and store it, and when we're reading, the value that's stored in the memory will be output onto those pins. And then there's really not that many pins left over. We just have chip enable and write enable and output enable. So it looks to be fairly simple to set up. And if we look at the second page of the datasheet here, it gives us a actual full pinout. And to make sure that we get the chip enable and output enable and write enable inputs set up correctly, we'll just follow along with this little truth table here on the bottom. So that way we can set it up to do exactly what we want. So let's pull our breadboard out, pop our chip in, and see what happens. All right, so here's the breadboard where we left off last time. You can see that we've got our clock over here and our program counter over here on the left. And there's currently power on, so it should still be working. Let's push the clock and find out. Yeah, that all seems to be, that's all working great. And we can halt it just like that. Yeah, that's all working awesome. All right, so we'll unplug power here. And let's go ahead and pop in our memory chip. All right, so normally I would say let's hook up power and ground first, but the power pin is right up here and there's going to be a whole lot of wires moving around in this area. So I'm going to save the power pin for a little later. But we'll hook up the ground pin, which is this one right over here. All right, so let's start with the data pins, and they're set up in a little weird manner. These 3 right here next to the ground are D0, 1, and 2, and then it kind of wraps around and we go 3, 4, 5, 6, 7, coming this way. So the least significant one is furthest away on this side, and the most significant one is furthest away on this side. And that's kind of confusing because I want to break them out into just a straight line. And so what I'm going to do is I'm going to run those pins over into this area because this is the area ultimately where we're going to put our dip switch that we're going to program the chip with. So let's go ahead and run the jumpers for that. All right, so that was a little convoluted, but we've got them all lined up right in a line here, and we'll build this out a little later. But let's focus on trying to get the rest of these pins hooked up. Now, because we only have an 8-bit address coming in, we need to pull address line A8 through A12 low. So I essentially just want that part of the address to always be 0. And A8, 9, and 11 are pins 25, 24, and 23. And then A12 is all the way over on the other side at pin 2. So let's go ahead and pull all of those to ground. All right, and then we have 4 more pins that we need to deal with. We've got 2 chip enable pins, a write enable, and an output enable. Now the first chip enable pin is right on the other side of the data pin here, and it is active low. And since we want the chip to essentially always be enabled, whether we're reading to it or writing to it, we need to pull that pin low. And because I'm going to have some other lines running through here, I'm going to use a slightly different shaped jumper to do that. All right, and then just on the other side of A10 here is the output enable, and it is active low as well. And so I think we want to pull this one low all the time too. But things are starting to get really full in here, and I want quick access to it in case I get something wrong. So I'm going to use a longer jumper for it to kind of run it over to ground a little further away. Now all the way at this far end here, we've got VCC, and then we've got a write enable and a chip enable 2. And the chip enable 2 is active high. So we're going to pull it up to VCC. All right, now a write enable is the big one. We want to be able to flip a switch for the write enable and either write to the RAM chip or let the RAM chip output. So we're going to run a jumper off of it all the way over to this kind of middle area over here so I can run a button on it. All right, and then so to turn the write enable on or off, I'm going to use a little toggle switch here, just like that. And then one part of that toggle switch is going to be pulled to ground. And then the other pin is going to be pulled high. So there we go. Now, depending on the position of this switch, we either have the chip set to write, so we can store whatever our dip switches are, or we can have the chip output that data onto the 8 bits that are going to feed the rest of the circuit. All right, so pretty much all that's left to hook up to this chip is the output coming from over here. So we somehow need to come down, around, and then to all of these pins on the bottom. It's in a really inconvenient spot. But I've got a bunch of jumpers that I've bent up roughly in the same shape, so hopefully we'll be able to get it to work. All right, so that's pretty unwieldy, but I think I've got all that hooked up correctly. But I'm going to run some jumpers over top of these to kind of help keep them in line. And that's actually where the VCC pin is going to do. It's actually going to jumper over all of that to help keep it in place, like that. And that should help keep some things organized, and it should also bring power to our chip here. Now I'm going to run another one of these organizational jumpers on the other side, but I'm not going to hook it up to anything. So I'm just going to skip this pin number 1 here, and I'm just going to go to ground. Just let it hold things like that. So that jumper doesn't actually jump or anything. It's purely just to hold these big yellow jumpers in place. All right, and while I'm putting things into this little power rail here, why don't we just go ahead and throw a little capacitor into it right there. All right, and so that should be our memory chip completely set up, except for the fact that we don't have a way to input any data into it or see what data is stored in it. And so that's where these 8 lines over here are going to come into play. I actually need these to go into 2 different directions. I need them to go over here for the dip switches, as well as come down this way for the remaining circuitry that we haven't built yet. And so I'm going to run some jumpers down to here so that we can have those lines for the future. All right, so next let's move all of these over here where I can access them a little better for the dip switches. All right, but now that we've got them all lined up, it means I can hook in the dip switch really easily. Now this end of the dip switch, all of these are just going to be pulled high. So I've got a bunch of little jumpers that I'm going to use for that. And then we'll just pull all of those high. All right, so now we have the ability to turn these on or off, but we still don't have any way to see what's on there. And so I need to move all of these one more step out so I can hook some LEDs up in this increasingly tight space right here. All right, now that we've got all those jumpers run right over to here, let's go ahead and plug our LEDs in right along here, but we're pretty tight on space. So I'm gonna move my power lines out of the way here. And we'll see if we can stuff them all in this tight little area right here. All right, so that wasn't exactly graceful, but I think I've got them all in place. except that the ground side isn't actually connected to anything. So let's run a bunch of jumpers and then ground that out as well. All right, and then the final step is that when we're writing to the RAM, we want to pull all of these lines low. And so what we're going to do is we're just going to put some pull down resistors on the lines right along here, just some little 1K resistors. All right, it's not graceful looking, but I think I've got all those hooked in correctly. And the idea is that whenever we're writing data into the static RAM chip over here, the dip switches essentially put those pins at floating. And so these 1000 ohm resistors will pull those inputs low without actually affecting the input during normal operation. All right, and I believe that's everything. So let's go ahead and hook power back up and see what happens here. Okay, so our program counter initialized into a random state, which, we were expecting. And the static RAM chip is actually displaying some data, which also is not unexpected. So if I just let the program counter run, we should see whatever random data is stored in the static RAM chip being displayed here. So let's give that a shot. Yeah, we can see that there's just some totally random data stored in there. All right. So now I want to clear out the static RAM chip. And I can do that by essentially just storing zeros for every address throughout our program counter. All I have to do is leave my dip switch off here and change this over to write. And when that happens, you can see that the LEDs go off because now it's writing whatever is being input into the data lines into the RAM chip here. So if I just let the clock run, that should store all zeros into every address in our RAM chip. So let's do that. Let's just crank the speed up. All right, so you can see that the program counter here has cycled through a couple of times. So we'll go ahead and halt it. We'll turn that off. And we'll reset back to 0. Okay, now we're reading the data that's in the static RAM chip. So if I let the program counter run, this should all stay off because we should have nothing but zeros stored into the static RAM chip. So let's give that a shot. Yeah, look at that. Okay, so we successfully stored nothing in our static RAM chip. Okay, so let's turn you off, reset you back to 0. We'll set you to write, and let's store a 1 into address 0 of our static RAM chip. So we'll just take our little dip switch here, flip you up. Okay, yeah, you can see we're displaying a 1. Now, if I go to the next clock cycle here, turn you off, and go back to read. Okay, yeah, you can see that we're still reading 0, but if I reset to 0, 0, 0, yeah, there we go. All right, so at address 0, we're storing a 1. So now we can program whatever 8-bit data we want into the static RAM here and correlate it to whatever program counter address we want. So let's program in something a little interesting. Okay, that's about all my fingers can handle of programming on that little dip switch. For more complex programs in the future, we're definitely gonna have to figure something else out. So we'll go ahead and pop you back over to read, reset, we'll halt it, get the clock going. All right, now when I undo this halt, we should see the program counter count up, and we should see some interesting patterns display on here. Let's see if it works. Yes, look at that. It's working. It's displaying all of the patterns that we programmed into it. Yeah. How cool is that? I'm so happy with that. That's really, really cool. And then we ran out. That was where my fingers got tired. So if we crank the speed up, it'll cycle back around, and we should see yes. The program cycle through so quickly, it just looks like random flashing lights. So let's reset. There we go. We've got a memory module that can store our programs, and then whatever data is being put out on these LEDs here is also being put out on these 8 jumpers here. And so we can pull those jumpers down to here and run them into the MC14500 as well as the input and output chips to control what's doing what in our computer. So we've got the primary fundamentals built now. So this turned out really, really good. I'm really happy with how this is working. And even though it's not a read-only memory, it still has the ability to carry the program that's going to run whatever it is that we want to run. And so we're starting to break our way into a system that has some form of capability. That's really cool. So in the next episode, we're going to pull out the MC14500 itself and actually get it onto the breadboard. But for now, I'm going to keep playing with this, maybe program in some more interesting patterns into our memory. But thank you all so much for watching, and we'll see y'all in the next episode.